Hi students, welcome to the 14th and last lecture in permutations and combinations. I hope you have enjoyed the course. So in this lecture I am going to discuss number of non-negative or positive integer solutions of an equation x1 plus x2 plus so on up to xr is equal to n. And I am going to give hints and solutions for the remaining problems in exercise 5. So because of lack of time, I am not revising all the concepts. So those who are interested, you can watch the previous video. In that video, I have revised almost all the topics in combinations. Before solving the remaining problems in the last exercise, let me introduce this interesting result. The number of non-negative integer solutions. Number of non-negative integer solutions of the equation x1 plus x2 plus x3 so on up to xr is equal to n is going to be n plus r minus 1, choose r minus 1. The proof of this result is not that hard. We can just use basic permutations and combinations to prove this result. Once we prove this result, we can use this result to find out number of positive solutions, and then we can use those things to solve few problems in the last exercise. So first try to understand the results. So first try to understand the question itself, the number of non-negative integer solutions of the equation. So let us try to understand the statement using an example. Suppose you have this equation x1 plus x2 is equal to 6. I want to find out the number of non-negative integer solutions. So let me write down the non-negative integer solutions. So 0, 6 is one solution and 6, 0 is the other solution. 1, 5 and 5, 1. 2, 4 and 4, 2. And then 3, 3. So these are the 7 possible solutions for this equation x1 plus x2 is equal to 6. Since it is a small equation, we can list down all the possible solutions and then we can count. What happens if I have this equation x1 plus x2 plus x3 is equal to 5? If I want to answer this equation, I can still list down all the possible options. But if I keep on increasing this n, or if I keep on increasing the variables, then it is not possible to write down all the solutions. So let us try to adapt a method to find out the number of solutions. Okay, so here we have x1 plus x2 is equal to 6. So for the time being, let us assume that these are the 6 sticks, 1, 2, 3, 4, 5, 6. Now let me introduce this star. If I put this star here, then number of sticks before this star is going to be x1, going to be the value of x1, and number of sticks after this star is going to be the value of x2. I can place this star anywhere in between these sticks or here or here. So all that I have to do is I can arrange these sticks and this star. So total I have 6 sticks and 1 star. I can arrange these 6 sticks and 1 star in a row in 6 plus 1 factorial ways. But unfortunately these 6 sticks are alike. Therefore I can divide it by 6 factorial. So which is going to be 7 factorial upon 6 factorial, which is going to be 7. So and these are my 7 solutions. Okay. Now x1 plus x2 plus x3 is equal to 5. So I have 5 sticks, 1, 2, 3, 4, 5. Now I have 3 variables x1, x2 and x3. So here what I am doing is I can introduce 2 stars. If I introduce star here and if I introduce star here, number of sticks before this star is going to be the value of x1, and number of sticks between these 2 stars is going to be the value of x2, and number of sticks after this star is going to be the value of x3. So here I have 2 variables x1 and x2 and I am using only 1 star. And here I have 3 variables x1, x2 and x3. I am using 2 stars. I can use this star anywhere in between these sticks or after these sticks. So if I write like this, star, star and then 1, 2, 3, 4, 5. Number of sticks before this star is 0. So x1 value is 0. Number of sticks between these 2 stars is 0. So x2 value is also 0. Number of sticks after this star is going to be 5. So x3 value is 5. So this this arrangement represents 0, 0, 5. Similarly, if I have 1, 2, 3, 4 star 1 star, then this represents the value of x1 is 4 and the value of x2 is 1 and the value of x3 is 0. All that we have to do to find out the number of non-negative solutions of x1 plus x2 plus x3 is equal to 5 is we have to arrange these 5 sticks and these 2 stars in a row. I can arrange these 5 sticks and 2 stars in a row in 5 plus 2 factorial ways. But unfortunately these 5 sticks are alike and these 2 stars are alike. So I have to divide it by 5 factorial times 2 factorial. So the answer is going to be 7 factorial upon 5 factorial times 2 factorial. So which is equal to 7 times 6 upon 2, which is equal to 21. So there are 21 possible ways of or 21 possible solutions of this equation x1 plus x2 plus x3 is equal to 5. So here we have 2 variables, I am using 1 star. Here we have 3 variables, so I am using 2 stars. So let us try to generalize this result. So number of non-negative solutions of the equation x1 plus x2 plus so on up to xr is equal to n is same as arranging n sticks and r minus 1 stars. This can be done in n plus r minus 1 factorial upon n factorial times r minus 1 factorial ways. Now n plus r minus 1 upon n factorial times r minus 1 factorial, I can write it as n, I am writing it as n plus r minus 1 minus of r minus 1 factorial times r minus 1 factorial. Now it is in the form of n choose r. So this I can write it as n plus r minus 1 choose r minus 1. So n plus r minus 1 choose r minus 1 is equal to n plus r minus 1 factorial upon n plus r minus 1 minus of r minus 1 factorial times r minus 1 factorial. Therefore, number of non-negative integer solutions of the equation x1 plus x2 plus so on up to xr is going to be n plus r minus 1 choose r minus 1. Okay. So let us improve this result, or let us have a corollary of this result. The number of positive solutions. So earlier we have find out number of non-negative integer solutions. Now we have to find out number of positive solutions. Number of positive solutions of the equation x1 plus x2 plus so on up to xr is equal to n is going to be n minus 1 choose r minus 1. So it is just a corollary of the previous result. So let us write down the equation x1 plus x2 plus so on up to xr is equal to n. I am rewriting this equation as, let us rewrite this equation so I can rewrite this equation as x1 minus 1 plus x2 minus 1 plus so on up to xr minus 1 is equal to n minus r. So here I have added r once, I have subtracted r once, so on the RHS also I am subtracting r. Now let me take, this is my y1 plus y2 plus so on up to yr is equal to n minus r. So let y1 is equal to x1 minus 1, y2 is equal to x2 minus 1, and so on up to yr is equal to xr minus 1. Now we have to find out number of positive solutions for this equation x1 plus x2 so on up to xr is equal to n. The number of positive solutions of the equation x1 plus x2 so on up to n, xr is equal to n, is same as number of non-negative solutions of this one. Number of non-negative solutions of y1 plus y2 plus so on up to yr is equal to n minus r. So let me write down the statement. Number of positive solutions of x1 plus x2 plus so on up to xr is equal to n is same as number of non-negative solutions so y1 plus y2 plus so on up to yr is equal to n minus r. And the answer for this one, number of non-negative solutions of y1 plus y2 plus yr is equal to n minus r is number of non-negative solutions of y1 plus y2 plus so on up to yr is equal to n minus r is n minus r plus r minus 1, choose r minus 1. So which is equal to n minus 1, choose r minus 1. So these are the total number of positive solutions of the equation x1 plus x2 plus so on up to xr is equal to n. So here we have proved two results. The first result is number of non-negative integer solutions of the equation x1 plus x2 plus so on up to xr. So the answer for this one is n plus r minus 1, choose r minus 1. So instead of non-negative, if I impose positive solutions, then the number of positive solutions is going to be n minus 1, choose r minus 1. So we are just manipulating the previous result. So we are writing this equation as in this way. x1 minus 1 plus x2 minus 1 plus so on up to xr minus 1 is equal to n minus r. Now I can take x1 minus 1 as y1, x2 minus 1 as y2, and xr minus 1 as yr. Now y1 plus y2 plus so on up to yr is equal to n minus r. The number of positive solutions of the equation x1 plus x2 so on up to xr is equal to xn is going to be same as the number of non-negative solutions of the equation y1 plus y2 plus so on up to yr is equal to n minus r. But we know the answer for this one. Number of non-negative integer solutions of y1 plus y2 plus so on up to yr is equal to n minus r is n minus r plus r minus 1, choose r minus 1, which turns out to be n minus 1, choose r minus 1. So these are the total number of positive solutions of the equation x1 plus x2 plus so on up to xr is equal to n minus r. Is equal to n. So let us try to solve this problem. Find the number of ways of giving away 4 similar coins to 5 boys, and each boy can receive any number of coins. Any number of coins instead, not more than 4. So find the number of ways of giving away 4 similar coins among 5 boys. Each boy can receive any number of coins. He can receive 0, or he can receive 1, 2, 3 or 4. But he cannot receive more than 4 because there are only 4 coins. Okay. Let xi stands for the number of coins received by the boy I. This implies x1 plus x2 plus x3 plus x4 plus x5 is equal to 4. x1 stands for number of coins received by first boy. x2 stands for number of coins received by second boy. x3 stands for number of coins received by third boy, fourth boy and fifth boy. Similarly, okay. Now x1 plus x2 plus x3 plus x4 plus x5 is equal to 4. Because sum of all the coins received by each boy is equal to total number of coins, which is nothing but 4. Okay. Now x1 can be 0. So first boy can get 0 coins also. So solving this question is same as finding the number of non-negative solutions of this equation. Number of ways of giving away coins is same as number of non-negative integer solutions. Solutions of x1 plus x2 plus so on up to x5 is equal to 4. But number of non-negative solutions of this equation is of the equation x1 plus x2 plus so on up to xr is equal to n is n plus r minus 1. Choose r minus 1. Here n is equal to 4 and r is equal to 5. So this implies 4 plus 5 minus 1. Choose 5 minus 1, which is equal to 8. Choose 4. Which is equal to 8 times 7 times 6 times 5 upon 24, 4 factorial. So 6 ones and 6 fours, 4 ones and 4 twos. So which is equal to 2 times 7 times 5, which is equal to 70. The number of ways of giving away 4 similar coins to 5 boys. Each boy can receive any number of coins is going to be 70. So we can generalize this result. Number of ways of giving away, instead of 4 coins, if you have 20 coins, or instead of 5 boys, if you have 7 boys or 11 boys or something like that, then you can solve this problem. So with the help of previous result, we can solve this problem easily. Okay, let us move on to the next problem. This is from third section, fifth problem. Okay. There are 8 railway stations on a railway line. In how many ways a train can stop at the 3 stations such that no 2 stops are consecutive? So let us try to understand the question. There are 8 railway stations in a railway line, and a train is supposed to stop at 3 of these stations. Now, in how many ways a train can stop at 3 of these stations such that no stops are consecutive? If it stops at station 1, it should not stop at station 2. It can stop at station 3 or 4 or 5, so on. If it stops at station 4, then immediately it should not stop at station 5. It should stop at station 6, 7 or 8. So try to understand the question. If you understand the question, then we can proceed to the solution. There are 8 railway stations along a railway line. Find the number of ways in which a train can stop at 3 stations so that no 2 stations or no 2 stops are consecutive. Okay, so let me write down the stations. Station 1, 2, 3, 4, 5, 6, 7, 8. There are 8 stations. Now a train can stop at 3 of these places. It can stop at station 1, it can stop at station 2, station 3, and so on up to station 8. But if it stops at station 1, it should not stop at station 2. If it stops at station 3, it should not stop at station 4. Okay. So the station where it stops is denoted by a star. Let us denote, or let star stands for the station where it is stopping, where the train is stopping. And 1 stands for the station where it is not stopping. So star stands for the station where it is stopping, and 1 stands for the station where it is not stopping. So if I have an arrangement like this, if I have an arrangement like this, 1, 2. So this is my station 1, station 2, station 3, station 4, station 5, station 6, station 7, and station 8. So it is stopping at station 2, and it is stopping at station 5, and it is stopping at station 7. Then station 1, it is not stopping, so I am denoting it by 1. Station 3, it is not stopping, so I am denoting it by 1. Station 4, it is not stopping, so I am denoting it by 1. Station 6, it is not stopping, so I am denoting it by 1. And station 8, it is not stopping, so I am denoting it by 1. So on the whole, we have 5 ones and 3 stars. Now let x1 denote number of stations before the first stop. And similarly, x2 denote number of stations between the first and second stop. And x3 stands for number of stations between second and third stop. And x4 stands for number of stations after third stop. So if you observe here, x1 plus x2 plus x3 plus x4 is going to be 5. So x1 plus x2 plus x3 plus x4 is going to be 5. But here this equation is little bit different. Why this equation is little bit different? Because let us see. So if the train stops at S1 and it is not stopping at S2, S3, and it is stopping at S4, and it is not stopping at 5, 6, 7, and it is stopping at S8. Now number of stations before the first stop is going to be 0, and number of stops between the first and second is going to be 2, and number of stops between second and third is going to be 3, and number of stops after third stop is going to be 0. So here x1 is equal to 0, x2 is equal to 2, x3 is equal to 3, and x4 is equal to 0. So x4 can take 0 values, can take the value 0. But x2 and x3 cannot take the value 0. Because between any two consecutive stops there should be one station. So x2 and x3 cannot take the value 0. But x1 and x4 can take the value 0. So if you understand this one, then we can write down the equation. Okay, let us write down the equation. We have x1 plus x2 plus x3 plus x4 is equal to 5. But here x1 and x4 can take the value 0. But x2 and x3 cannot take the value 0. So in order to solve this equation x1 plus x2 plus x3 plus x4 is equal to 5, I cannot use the number of non-negative solutions, nor I cannot use number of positive solutions. So I have to readjust this equation. So solving this equation is same as solving equation 1. So let me write, this is my equation 1. Equation 1 is same as to solve x1 plus x2 minus 1 plus x3 minus 1 plus x4 is equal to 5 minus 2. Now this is my y1 plus y2 plus y3 plus y4 is equal to 3. So y1 plus y2 plus y3 plus y4 is equal to 3. Now I can apply number of non-negative integer solutions for this one. So I cannot apply number of non-negative integer solutions for this one, nor I cannot apply number of positive solutions for this equation. But for this equation I can apply number of non-negative integer solutions. And number of non-negative integer solutions for this equation is number of non-negative integer solutions is 3 plus 4 minus 1 choose 4 minus 1, which is equal to 6 choose 3. So if you want, you can expand this one. It is going to be 6 times 4, 5 times 4 upon 6, which is going to be 5 times 4, which is 20. So the number of ways in which a train can stop such that no two stops are consecutive is going to be 20. So let me explain the problem again for you. So this problem is a little bit tricky. So we have 8 railway stations along a railway line, S1 to S8. A train can stop at 3 of these stations. The condition here is no two stops should be consecutive. So let's star denote the station where it is stopping and 1 denote the station where it is not stopping. So I can have this kind of arrangement. So here the train is stopping at 2nd station, 5th station and 7th station. And remaining stations it is not stopping. So on the whole we have 3 stars and 5 ones. And now let x1 denote the number of stations before the first stop, x2 denote the number of stations between the first and second stop, x3 denote the number of stations between second and third stop, x4 denote the number of stations after the third stop. But here there is a catch. The catch is x1 and x4 can take the value 0. x1 and x4 can take the value 0. Because if the train stops at the first station and in between 4th station and 8th station, if the train stops at first station, then the number of stations before the first stop is going to be 0. And if the train stops at 8th station, then the number of stops after 8th station is going to be 0. So x1 and x4 can take the value 0. But x2 and x3 cannot take the value 0. So I cannot apply number of non-negative integer solutions for this equation, nor I cannot apply number of positive solutions for this equation. So this equation I am just rewriting like this. So why I am rewriting like this means, after rewriting I will have this equation. For this equation I can apply number of non-negative integer solutions. If y1 is, y2 is equal to 0, then x2 minus 1 is equal to 0. That means x2 is equal to 1. So even if y2 is equal to 0, x2 cannot be 0. Even if y3 is equal to 0, x3 cannot be 0. So after rewriting this equation, I have y1 plus y2 plus y3 plus y4 is equal to 5. Now I can apply number of non-negative integer solutions for this equation. And the number of non-negative integer solutions for this equation turns out to be 3 plus 4 minus 1, choose 4 minus 1, which is equal to 6, choose 3, which is equal to 20. Therefore, there are 20 ways in which a train can stop at 3 stations out of 8 such that no 2 stops are consecutive. So these two problems are little bit tricky. Many people face a lot of difficulty in solving these two problems. And these two problems can be immediately solved using these two results. Number of non-negative integer solutions and number of positive solutions. Number of non-negative integer solutions is going to be n plus r minus 1, choose r minus 1. And number of positive solutions is going to be n minus 1, choose r minus 1. So if you understand the proofs of these results, then you can, there is no need to remember the results. You can just derive it. Anyway, those who are not interested in the proof, they can just remember the results. If you remember the result, you can answer these two questions easily. The number of ways of giving away 4 similar coins to 5 distinct boys, and the number of ways a train can stop at 8 of these stations. A train can stop at exactly 3 of the 8 stations such that no 2 stops are consecutive. And the next question is like this. Prove that 4n choose 2n upon 2n choose n is equal to 1 times 3 times 5 so on up to 4n minus 1 upon 1 times 3 times 5 so on up to 2n minus 1 whole squared. I repeat, 4n choose 2n upon 2n choose n is equal to 1 times 3 times 5 so on up to 4n minus 1 upon 1 times 3 times 5 so on up to 2n minus 1 whole squared. So there is nothing much in this problem. You have to be little bit careful in calculation. So 4n choose 2n upon 2n choose n is equal to 4n factorial upon 4n minus 2n factorial, which is going to be 2n factorial times 2n factorial divided by 2n factorial upon 2n minus n, which is n factorial times n factorial. So which I can write it as 4n factorial upon 2n factorial times 2n factorial times n factorial times n factorial upon 2n factorial. So on the RHS, in RHS we have product of odd terms both in the numerator and denominator. So first let us try to expand this 4n factorial. So this 4n factorial I can write it as, I am expanding in the reverse way, so 4n factorial I can write it as 1 times 2 times 3 times 4 so on up to 4n. So before 4n I will have 4n minus 1, okay, upon 2n factorial. So 2n factorial I can write it as 1 times 2 times 3 so on up to 2n minus 1 times 2n. So we have 2n factorials or 2n factorials. We can write it as whole cube, or let me write it as 2n whole square into 2n factorial. I am keeping this 2n factorial as it is, and then n factorial times n factorial. So n factorial means I will have 1 times 2 times 3 so on up to n whole square. Okay, so I want to have only odd terms. So for this what I can do is I can remove all even terms. Removing all even terms means I can write down all even terms one side and all odd terms one side. So which is equal to So out of 4n numbers, how many numbers are even and how many numbers are odd? So there are exactly half of the numbers which are even and half of the numbers which are odd. So first let me write down the odd numbers, which is equal to 1 times 3 times 5, so on up to 4n minus 1. So these are my odd numbers. And what are my even numbers? 2 times 4 times 6, so on up to 4n. These are my even numbers upon. So here also I have 1 times 2 times 3, so on up to 2n. So let me write down all odd terms. 1 times 3 times 5, so on up to 2n minus 1, and then 2 times 4 times 6, so on up to 2n whole square into n factorial, okay, whole square upon 2n factorial. Now here we have 2 times 4 times 6, so on up to 4n. So how many odd terms are there and how many even terms are there? That is the question. So number of odd terms is going to be 2n and number of even terms is going to be 2n. So here you have 2n even terms. What are those 2n even terms? These are my 2n even terms. Let me expand these things, or let me rewrite that one. So 2 times 4 times 6, so on up to 4n. I can write it as, so from this 2 I am taking 1 2 common, so it is equal to 1. From this 4 I am taking 1 2 common, so it is going to be 2. From this 6 I am taking 1 2 common, it is going to be 3, and so on up to, from this 4n I am taking 2 common, so which is going to be 2n. So on the whole I am taking 2 out from each term. So there are 2n terms, so I will be having 2n 2 terms, so which is going to be 2 power 2n. So if you understand this one, then you can solve the problem easily. So here we have 2 times 4 times 6, so on up to 4n. So 2 times 4 times 6. So from these 3 terms I can take 1 2 common, another 2 common from 4, another 2 common from 6, and another 2 common from 4n. So if I keep on removing 2 from every term, I will be having 2n 2's, which turns out to be 2 power 2n. And the remaining terms are going to be 1 times 3 times 5, so on up to 2n. 1 times 2 times 3, so on up to 2n. So which is nothing but 2n factorial. So this I can write it as 2n factorial times 2 power 2n. So on the whole what I have is, okay, and in the denominator I have 1 times 2 times, so on up to 2n, or 2 times 4 times 6, so on up to 2n. This I can write it as 1 times 2 times 3, so on up to n times 2 power n. So here I have n terms, which are 2, 4, 6, and so on up to 2n. These are n terms. Out of these n terms, I am taking 2 common from each term. If I take 2 common from each term, I will have 2 power n. And the remaining terms are going to be 1 times 3 times 5, so on up to n, or 1, 2, 3, so on up to n, which is nothing but n factorial times 2 power n. So let us substitute these things in the previous equation. So in the previous equation, there is nothing to change about this bracket, and coming to this bracket I can write it as 2n factorial times 2 power 2n. 2n factorial times 2 power 2n. And then coming to this bracket 1, 3, 5, there is nothing to change. And coming to this bracket 2, 4, 6, and so on up to 2n. This bracket I can write it as 1 times 2 times 3, so on up to n times 2 power n. So which is nothing but n factorial times 2 power n. But here we have whole square. So let us write down all these things. So which is equal to 1 times 3 times 5 so on up to 4n minus 1 times, so this term 2 times 4 times 6 so on up to 4n. This I can write it as 2n factorial times 2 power n. This is nothing but 2n factorial times 2 power 2n by 1 times 3 times 5 so on up to 2n minus 1 whole square, and instead of the next term I have n factorial whole square times 2 power n whole square, which is nothing but 2 power 2n into n factorial whole square upon 2n factorial. So this 2n factorial and this 2n factorial gets cancelled, and this n factorial squared and this n factorial square gets cancelled. So what is left out is 1 times 3 times 5 so on up to 4n minus 1. It is our numerator. And what is our denominator? Denominator is going to be 1 times 3 times 5 so on up to 2n minus 1 whole square. And this is going to be our RHS. And the next question is like this. If a set A has 12 elements, find the number of subsets of A having 4 elements, and the next one is at least 3 elements, and the next one is at most 3 elements. So in order to answer this question, what you have to do is you should know the meaning of these two terms, at least 3 elements and at most 4 elements. And you should know one more thing. Number of subsets of a set having n elements is going to be 2 raised to n. The number of subsets of a set having n elements is going to be 2 raised to n. If you want to discard empty set, then it's going to be 2 raised to n minus 1. So we have proved this result in the last class, or last class means in the previous class. So if you know those two things, then you can easily answer this question. So first let us answer the first one. Number of subsets with 4 elements. Number of subsets with 4 elements. Number of subsets of a set with, number of subsets with R elements of a set with n elements is going to be n choose R. So here we have to select a set, here we have to find the number of subsets of a set A with 12 elements having 4 elements. We have to form 4 element sets. So number of subsets with 4 elements is going to be, this is 12 choose 4. So we are using this result. N choose R stands for number of subsets with R elements of a set having n elements. So if you know this result, then you can answer the first one. Now let us answer the second one. Second one is at least 3 elements. At least 3 elements means exactly 3 plus exactly 4 plus exactly 5 plus so on up to exactly 12. That is exactly 3 plus exactly 4 plus exactly 5 so on up to exactly 12. So you have to add up all these things. So you know how many number of subsets are there which having exactly 3. So which is equal to 12 choose 3 plus 12 choose 4 plus 12 choose 5 plus so on up to 12 choose 12. You can leave the answer as it is. You can answer the same question little bit differently. So here the question is at least 3 elements. The total number of subsets is going to be 2 power n. So you can answer this question in another way, or total subsets is equal to 2 power 12. Number of subsets with 0 elements is 0 elements is 12 choose 0, which is equal to 1. Okay, no need to expand that one. And number of subsets with 1 element is 12 choose 1. And similarly, number of elements with 2 elements, number of subsets with 2 elements is going to be 12 choose 2. So total minus these things, number of subsets with exactly 1 element, number of subsets with 0 elements, 1 element and 2 elements. If I remove these 3, then I am going to get number of subsets with at least 3 elements. So answer is 2 power 12 minus of 12 choose 0 plus 12 choose 1 plus 12 choose 2. So you can leave the answer as it is like this, or else you can do it in this way. So you can solve the problem in 2 ways. The first one is to find the number of subsets with at least 3 elements. At least 3 elements means there can be 3 elements or 4 elements or 5 elements, so on up to 12 elements. So number of subsets with 3 elements is going to be 12 choose 3. 4 elements is going to be 12 choose 4, and so on up to 12 elements is going to be 12 choose 12. So you can leave the answer as it is, or else what you can do is you can solve the problem in another way. Another way is the total number of subsets is going to be 2 raised to 12. Number of subsets with 0 elements is going to be 12 choose 0, which is 1. Number of subsets with 1 element is going to be 12 choose 1. Number of subsets with 2 elements is going to be 12 choose 2. So number of subsets with at least 3 elements means total number of subsets minus number of subsets with 0 elements plus number of subsets with 1 element plus number of subsets with 2 elements. So both the answers are correct. Now let us answer the third one. The third one is number of subsets with at most 3 elements. So we have answered the first two with exactly 4 elements with at least 3 elements, and the next one we have to answer is at most 3 elements. At most 3 elements means it can have 0 elements or 1 element or 2 elements or 3 elements. At most 3 elements means it can have either 0 or 1 or 2 or 3. So number of subsets with 0 elements is going to be, that is 12 choose 0 plus 12 choose 1 plus 12 choose 2 plus 12 choose 3. At most 3 elements means it can have 0 elements or 1 element or 2 elements or 3 elements. So this is the answer for the third one. The next question is like this. If 5 vowels and 6 consonants are given, how many 6-letter words can be formed using 3 vowels and 3 consonants? So you have to understand this question before answering this one. So if I have only 3 vowels and 3 consonants, then the number of 6-letter words is going to be 6 factorial. But here I am having 5 vowels and 6 consonants. And I have to form 6-letter words which have exactly 3 vowels and 3 consonants. So my W1 is to select 3 vowels from 5 and 3 consonants from 6. and this W number of ways of doing W1 is, okay, 5 choose 3 times 6 choose 3. W2 is to arrange to form 6 letter words using the 6 selected letters. This W2 can be done in 6 factorial ways. So number of ways of completing the task is equal to number of ways of doing W1 times number of ways of doing W2, which is equal to 5 choose 3 times 6 choose 3 times 6 factorial. So you have to just remember the double-decker bus. In the double-decker bus, what you have done so first you have distributed the people to the lower deck and upper deck, and then you have arranged them. So here also first you have to select 3 vowels and 3 consonants. That can be done in 5 choose 3 times 6 choose 3 ways. After selecting, you have to arrange. You can arrange them in 6 factorial ways. So all that you have to remember in this question is you have to understand the question. So if you understand the question, then you can answer the question easily. Let us solve this question. A question paper is divided into 3 groups A, B and C with 3, 4 and 5 questions respectively. Find the number of ways of attempting 6 questions, choosing at least one from each group. So try to understand the question. So there are 3 groups in the question paper, A, B and C. A has 3 questions, B has 4 questions and C has 5 questions. On the whole, the question paper has 12 questions, 3 plus 4 plus 5. So out of these 12 questions, you have to attempt 6. And you are not supposed to answer any 6. You are supposed to answer at least one question from each section. You are supposed to answer 6 questions, and out of those 6 questions, you have to include one question from each group. Okay. So total number of questions is equal to 3 plus 4 plus 5, which is equal to 12. And you have to answer 6. You have to answer 6. This can be done in 12 choose 6 ways. But all these choices are not desirable. So we have to answer at least one question from each section. So for this, what we are doing is, if I don't answer any question from A, that is not a desirable thing. Number of ways of answering 6 without a question from A. Is, so I should not select any question from A, so I have to select the remaining 6 from B and C. So is 4 plus 5 choose 6, which is equal to 9 choose 6. Similarly, without any question from B, without anything from B is going to be 3 plus 5 choose 6, which is equal to 8 choose 6. And similarly, without any question from C is equal to 3 plus 4 choose 6. So all these 3 choices are not desirable. Out of the total 12 choose 6, this way and this way, these 3 ways are not desirable. Therefore our answer is, so these 3 are not desirable. These 3 are not desirable. Therefore, number of ways of answering is equal to 12 choose 6 minus 9 choose 6 plus 8 choose 6 plus 7 choose 6. So we have to remove these three non-desirable ways. If you remove these three non-desirable ways, the rest of them are desirable ways. In the remaining ways, you can answer 6 questions with at least one question from each group. Find the number of ways in which 12 things can be divided into 4 equal groups, can be distributed among 4 persons equally. So there are 12 distinct things. Now you have to divide these 12 distinct things into 4 groups equally. And the next thing is we have to distribute them among 4 people equally. So we have these results. Number of ways of dividing mn distinct things into m groups, each containing n elements, is going to be mn factorial upon m factorial times n factorial raised to m. N factorial raised to m. These are the number of ways of dividing. Number of ways of distributing is going to be mn factorial upon n factorial raised to m. So here you have m is equal to 4 and n is equal to 3. So if you apply these two formulas, then you can answer this question easily. So all that you have to do is you have to remember these two formulas. Number of ways of dividing mn things number of ways of dividing mn things into m equal groups, each containing n elements, is going to be mn factorial upon m factorial times n factorial raised to m. And number of ways of distributing mn distinct things among m people equally is going to be mn factorial upon n factorial raised to m. So here in this case we have 12 things and we have to divide it into 4 groups. So number of groups is equal to 4, so m is equal to 4. So mn is equal to 12, therefore n is equal to 3. So if you remember these two results, then you can answer it easily. Let us move on to the last question. The last question is like this. A class contains 4 boys and G girls. A class contains 4 boys and G girls. Every Sunday, 5 people with at least 3 boys go for a picnic. And each time a different group is selected to go for a picnic. If the class teacher distributes a doll to each girl in the group, and if he distributes 85 dolls, then find the number of girls in the class. So a class contains 4 boys and G girls, and each Sunday 5 students will go to picnic with at least 3 boys. And at the picnic spot there is a class teacher who will give dolls to every girl in that group, and on the whole he have distributed 85 dolls. Now you have to find how many girls are there in the class. So this is little bit tricky. If you write this equation, then it will be easier. So number of students in the picnic is going to be 5, and there are at least 3 boys. At least 3 boys means exactly 3 boys plus exactly 4 plus exactly 5, but there are no but the class contains only 4 boys, so exactly 5 I cannot have. So exactly 3 boys plus exactly 4 boys. Exactly 3 boys, so already 3 boys are there, I have to select 2 more. So I can select 3 boys from 4 in 4 choose 3 ways, and I can select 2 more girls from G girls in G choose 2 ways. Exactly 4 means I can select 4 boys out of 4 and I can select 1 girl from G girls. So exactly 3 ways, exactly 3 boys, these many groups are there. Exactly 4 boys, these many groups are there. In this group there are 2 girls. So if this group goes to the picnic, so teacher has to give away 2 dolls. If this group goes for picnic, then teacher has to give away 1 doll. So this implies number of dolls distributed by teacher is equal to 4 choose 3 times G choose 2. If this group goes to picnic, he has to give away 2 dolls, plus 4 choose 4 times G choose 1 times 1. If this group goes to a picnic, he has to give away 1 doll. So the total number of dolls that he had distributed is equal to this one. But we know the value of, but we know how many dolls he have distributed. But number of dolls distributed is equal to is equal to 85. So this implies 4 choose 3 times G choose 2 times 2 plus 4 choose 4 times G choose 1 times 1 is equal to 85. 4 choose 3 is same as 4 choose 1, which is equal to 4. 4 times G choose 2, which is G times G minus 1 upon 2 times 2 plus 4 choose 4 is 1 and G choose 1 is G times 1 is equal to 85. So this implies 4 times G minus 1 plus G is equal to 85. So which is 4G square minus 4G plus G, which is going to be minus 3G minus 85 is equal to 0. So you have to factorize this one. So 4G square minus 20G plus 17G minus 85 is equal to 0. So 4G times G minus 5 plus 17 times G minus 5 is equal to 0. So you have 4G plus 17 times G minus 5 is equal to 0. So G is equal to minus 17 upon 4 or G is equal to 5. But G stands for number of girls. Number of girls cannot be a negative or cannot be a fraction. Therefore G is equal to 5. So the total number of girls in the class is going to be 5. So if you can able to write down this equation, then things will be easier. So all that you have to do in this question is you should be in a position to write down this equation. So exactly 3 boys can go to the, at least 3 boys should be there in the picnic, means there can be exactly 3 boys or exactly 4 boys. So with exactly 3 boys, these many groups we can have. With exactly 4 boys, with these many groups we can have. So number of dolls that he have distributed is equal to, so if this group goes, he have to distribute 2 dolls. If this group goes, he have to distribute 1 doll. So number of dolls is equal to 4 choose 3 times G choose 2 times 2 plus 4 choose 4 times G choose 1 times 1. But we know the exact number. Exact number is going to be 85. Therefore, we have this equation. 4 choose 3 times G choose 2 times 2 plus 4 choose 4 times G choose 1 times 1 is equal to 85. So if you simplify, you will have this quadratic equation. For this quadratic equation, you have these two as roots. But here G stands for number of girls. Number of girls cannot be negative or number of girls cannot be a fraction. Therefore, G has the only one option, that is G is equal to 5. Therefore, number of girls in the class is going to be 5. With this, we have completed permutations and combinations.